Let us prove by mathematical induction that 1 plus 2 plus 3 plus dot 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 n is less than 2n plus 1 whole thing square. This involves three steps. First one is the statement. So we frame the statement. Let Pn be the statement 1 plus 2 plus 3 plus dot 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 n is less than 2n plus 1 whole thing square. Second step, it involves starting point, and third step, it involves the cycle. So we start with n equal to 1. Therefore, if Pn is the statement, what is P1? Therefore, P1 is the statement. We need to show that starting point is true. If we cannot start it, then of course we cannot continue it. So we should be able to show that we can at least start it. P1 is the statement. We just write n equal to 1. 1 is less than 2 times 1 plus 1 whole thing square. Is that true? 2 1 is 2 plus 1 is 3 square is 9, which is true. So far we can say that this statement is true for n equal to 1. At least we have one value of n for which it is true. Let us assume that Pn is true for some n equal to k. So we assume that Pn is true for some n equal to k. We want to get some kind of cycle. So in order to prove something, we need to assume something. So we are assuming that Pn is true for some n equal to k. At least we have shown that Pn is true for n equal to 1 or k equal to 1. So we have assumed something, and with that assumption we will prove something. So let us continue it. So we are assuming Pn is true for n equal to k. We will show that Pn plus 1 is true or Pk plus 1 is true whenever Pn is true. Let's do it. Then 1 plus 2 plus 3 plus dot 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 plus k plus 1. We want to show that Pk plus 1 is true or Pn is true for n equal to k plus 1. But Pk plus 1 in left hand side of the inequality involve 1 plus 2 plus 3 plus dot 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 plus k plus 1. And since we are assuming this is to be true, this is less than, we are assuming Pk is true or Pn is true for n equal to k. So instead of n we can write k and say that 1 plus 2 plus dot 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 plus k is less than 2k plus 1 whole thing square. This is less than 2k plus 1 whole thing square plus k plus 1. We copy as it is. Why is this true? By our induction assumption. The reason is by our induction assumption. So in order to obtain something, we need to assume something. We are assuming that Pk is true, that is 1 plus 2 plus 3 plus dot dot k is less than 2k plus 1 whole thing square, and then k plus 1 we copy as it is. And we want to show somehow that Pk plus 1 is true, that is 1 plus 2 plus 3 plus dot 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 k plus 1 is less than 2 times k plus 1 whole thing square. Now this is equal to 2k plus 1 whole thing square, that's 4k square plus 4k plus 1 plus k plus 1. That's equal to 4k square plus 5k plus 2. Somehow we want to show that this quantity 1 plus 2 plus 3 plus dot dot plus k plus 1 is less than, if we write n by k plus 1, 2 times k plus 1 whole thing square. Let's do some rough work. 2 times k plus 1 whole thing square. How much is that? That's equal to 2k plus 2 plus 1. That's equal to 2k plus 3 whole thing square. That's equal to 4k square. We use the formula a plus b whole thing square equal to a square plus 2ab. So 2 times 2 is 4, 4 plus 3 is 4 times 3 is 12, 12k plus 9. So we should be able to show that this is less than 4k square. That's obvious, in fact equal, plus 5k. 5k is definitely less than 12k, and 2 is definitely less than 9. So 4k square plus 5k plus 2 is less than 4k square plus 12k plus 9. That's obvious for k equal to 1, 2, 3, 4, and so on. Okay, so what do we get? We get that pk plus 1 is true. Therefore, pn is true for n equal to k plus 1. But that is true with the assumption that whenever pk is true. So what do we obtain? We obtain that whenever pk is true, comma, with that assumption we can say that pk plus 1, whenever pk is true, comma, pk plus 1 is also true. So if we take k equal to 1, so p1 is true, imply p2 is true. We just take k equal to 1. Again, if I take k equal to 2, p2 is true, imply p3 is true. Again, if I take k equal to 3, p3 is true, imply p4 is true. What does it mean? By taking case, we further and further, we find that pk is true for every k. So by principle of mathematical induction, Pn is true for every n. Once again, Pn is true for every n, comma, n equal to 1, 2, 3, 4, 5, and so on. And we are done.